Good morning, everyone. Welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. The primary purpose of this series is to cover a bit more in depth on the application of the tools towards a number of topics, and as such, we may not necessarily have an exhaustive reflection on the technical aspects of the system, but more so the features of the tools that might help you be more productive or do your job better. So hopefully, as we bring up the refresher of your knowledge, you will be able to see more ability to use the tools going forward. So as we are in the habit of doing, we like to start each session with a poll question. And so we've got a couple of new ones that we'd appreciate your participating in. The first is, how often do you coordinate ground fault protection devices in the projects that you work? So again, no obligation, but some feedback would be appreciated. And I very much value the communications with the audience. As I often repeat, you are where the rubber meets the road in this part of the industry. And so the feedback you provide is extremely valuable to me in being able to amplify the application of the tool. So we've got about 2/3 of a quorum. Let's leave this open for another 10 seconds. Let's close this out now. Thank you. Here's how people have weighed in on the topic. So a good distribution, and I'm a little bit surprised at the amount of folks that never have to do coordination on ground, but I think that kind of comes into play. So next question is, how frequently do you see resistance grounded systems? And again, this is one that there's been kind of an ebb and flow of popularity. There was a time when very, very few systems would be resistance grounded. And then back in the 80s, it became a more commonly seen application of the technology. And as new technologies are evolving, I think there's a potential to see it more frequently even now. So we have about 2/3 of a quorum. Let's leave this open for another 10 seconds. So here's how folks have weighed in on this. So roughly half of the applications encounter resistance grounded systems often. Good to know. Again, thank you for attending and thank you for sharing your experience. And let's talk about today's agenda. So the most common fault in the industry is a grounding fault. And this can be a gradually increasing situation, or it can be a radical event that causes problems. But in any case, bad things can result as grounding systems fail. There's ground protection fails. And so what we're going to look at today is two applications of the tools. One where we have ground fault protective device coordination in a resistance grounded system on the neutral leg of the transformer, and then one where we don't, where we have more hard grounded systems in a low voltage application. So neutral resistance ground has some key benefits, especially when used in a medium voltage arena or section of the system where there's a fairly hefty cost to the equipment, both in downtime and repair or replacement. And so the benefits of neutral resistance grounding is to reduce equipment damage and potentially extend the life of the transformer, because now you're limiting the amount of fault current that can go through the transformer on a ground fault. Has the potential for reducing the operation and maintenance costs, and potentially reduce unplanned shutdowns because a catastrophic event can be avoided. Makes it a little easier to debug ground faults and detect them early. So there's some advantages utilizing the neutral ground technology or application. And one of the things you'll see as we get into EasyPower is by reducing or inserting a resistance in the ground leg or the neutral leg of the transformer, we eliminate the need to worry about phase shifting or derating the single phase to ground current, because rather than the tens of thousands of amps that we would potentially see in a hard grounded system, we have the ability to reduce that to a max limit on the current itself. So the industry standard when we're applying this application of ground system protection is to use 50G ground relays as a first instantaneous set for the first level of protection on the feeders or on the loads. And in this case, we're looking at probably medium voltage motor controllers or transformer protection downstream. And then to have neutral overcurrent protection as the main protection for the subsystem or switchboard or motor control center. So these aren't backup. These are literally zone protection devices. So we may have multiple 50G relay settings on each of the feeders, and then only one 51N neutral overcurrent, and it has the ability to trip either the switchboard main or potentially the main based upon how extensive the load on the switchboard that we're trying to protect. And then the final level of protection on the whole system is the 51G relay on the neutral current itself. And so let's see what we can do to kind of set this up in my example. The suggested guidelines would be to have the neutral resistance value be somewhere in the 100 to 400 amp range for 2.4 to 4.1 kilovolts. So in this example, we're going to be using a 400 amp resistor or 400 amp system. The CT rating for the zero sequence CT will be 50 to 5, and then for the neutral ground, it's going to be 50% of the rating of the resistor itself. 50G we're going to pick up at 5 amps, so it's pretty much instantaneous. 51N pick up at 25% of the max rating, so it'll be somewhere around 100 amps, and then set the time dials for in progressive order going upstream from a 51N to the 51G. So let's see what this looks like in EasyPower. So again, what we have are a series of zones. We've got our neutral resistor relay set up on a 50% range on the CT. A couple points to be made. If we go into coordination, we're going to set, and we want to make sure we look at a single line to ground fault. If I fault this downstream load or downstream bus, looking at current, the tool will show me my sequence of events, and it indicates that this relay is set to trip at 16 milliseconds, and this one is going to trip at roughly 99 milliseconds, but it's indicating red because there's a potential out of order detected. And so what we would prefer to have is our feeder relay trip first, the neutral relay trip second, and then the ground relay trip last. So let's look at the TCC curves and see what we've got going on. So let's pick up this part of the system, this part of the system, and plot the TCC curves. All right, if we can change the set points on our system by using the setup dialog box for the relay, or we can do it on the TCC curve. And so if we want to set our zero sequence at actually, if we want to set our zero sequence to trip instantaneously, we set this up for 5 amps. So our relay, if we come up and find the tick mark, and we see it set at 5 amps. We can change it, but let's go ahead and leave it at 5 amps for now. Then this relay, the neutral relay, we want to set that up at 25%. So we've set this up for 100 amps. 51N is right here. We can see it's set for 90 amps. Let's go ahead and so that's at 100. And then we want to set up the 51G at 100 as well. Now, if you can see the little inset box, you can see what I'm dialing into it to get there. Now we want to adjust the time delay. And on the 51N, we want the time dial set at, let's start at 1, which is where it is. And let's see if we can get that. The 51G set at 2, so let's reverse them. All right, so there's 51. Now, obviously, this is a little gross or coarse as far as my ability to roll the mouse, and so I probably want to open up the dialog box and get it more specific. But for now, I've got this set for a time dial of 1, and this set for 1.99. Now, when we have a fault on this bus, we can see, now we're looking at the current through each of the trip devices. If we want to separate those, we'd set them up at different times. So let's open up this dialog box for the feeder and leave its dial setting at momentary. Open up the dialog box for this neutral. Let's set it up for 30 cycles to tick mark. It'll be the same current because the ground current has a maximum of 400 amps. And then the same thing here. Let's set this up for 30 seconds, 30 cycles. I can get there. Now, if we want to, now both of these are set up. Let's go back and look at this. Both of these are set up for shape that we want to basically match. So very inverse is the shape of the curve for the 51G. Time multiplier, let's go ahead and set it at 2.0. And disable the instantaneous and the 51N. Let's make sure it's set for very inverse and set for a dial setting of 1. And there we have pretty decent coordination. The other significance is the tool has the ability to pick up on lower current and trip an individual section as a result. And so this makes it easier to troubleshoot if we have a low-level ground current before it elevates into a worst case situation. Okay, so let me see if we got questions. All right, so that's the medium voltage settings, and we're happy with that. Let's go on and move it to solidly grounded. So this is more difficult when things are in a low voltage system, especially if we're using multi-case circuit breakers, because they have an instantaneous trip that's in effect full time. Coordination usually requires a trip unit, a solid state trip unit that has the ability to program in extra functions besides and override the instantaneous trip, or at least adjust it. So the NEC requires ground fault protection on service rated over 1,000 amps, and feeder breakers with ground fault protection really are no issue as far as being able to coordinate with them. The issues arise when we're using fuses that are greater than 100 amps and multi-case circuit breakers greater than 50. Now, the device library in EasyPower actually lists a combination of upstream and downstream breakers which the manufacturer has tested and will support coordination. And so let's see if we can't demonstrate that. And in addition, the sequence of events gives us a quick snapshot of coordination. So what we're going to look at is a ground system that has 51G functionality at the main. On the feeder breakers, have a minimum setting for ground fault and the potential for having an in and out tick mark or adjustment to include fuses. So let's see what this looks like in EasyPower. Now, I mentioned, I'm going to go ahead and close this. Project. Now I mentioned that in the library, so for instance over here we have installed a square D PK device, and we want to know what it would take to coordinate with it downstream on this particular load. And so if we go to the EasyPower device library and look up the PK, so I'm in the device library, square D, P-frame, the PK element with the 1200 amp sensor, we can look up series coordination, and it gives us a list of breakers that can be used downstream and their sensor or trip settings that they guarantee or suggest we can do or realize coordination. So as we're doing that, here's what it looks like in the application. So let's go into coordination. Let's look at a single bus fault, looking at current, and our sequence events. Indeed shows that we have a 17 millisecond downstream trip and a 32 millisecond or 320 millisecond trip on the upstream. So in fact, we do have coordination. How that looks, we don't need to include the transformer. How it looks is a little bit different. And if we plot the TCC, we see the adjustment has been made on the upstream device to allow coordination on this bus faulted downstream. And so we see, we recognize an advantage there. Now, what I was reporting or referring to on the I squared T element, if we look at the set points for this upstream device, it has a more sophisticated trip unit associated with it. It has the ability to, on my ground trip, maybe it doesn't, now that I look at it, include or not include an I squared T function. So this doesn't include it. Let's see if we can find it on another breaker. So in any case, the adjustment would be made with the this breaker threshold for short-term pickup. Again, these adjustments aren't available in molded case circuit breakers without a trip unit either shunted or added to the device. So let's look at this section. Let's go ahead and do a short circuit first. This bus were to fault, we'd see we have the fuse tripping in 10 milliseconds, the upstream breakers tripping at 440 milliseconds. And if we demonstrate these TCC curves, we can see in fact that is the case. Now we only want to look at the ground trip coordination. So let's take off the tidal block on the one line, and we can see for a fault downstream that the fuse trips first. Now clearly these aren't coordinated for a lower current fault level, but at the worst case they do have coordination. So let's call that good. Let's look at this. And again, it's important to notice that I'm looking at just the ground fault. We have a single phase fault line to ground or single line to ground fault. And so this gives us the ability where we want the first BL4 to trip first. We can see that it's actually not tripping first over the full expanse. So to get coordination, better coordination, I would probably end up having something that looks like this. And then finally on the coordinating with the motor protection circuit, we plot the TCC and look at just the phase, the ground coordination. We can see that for a single line to ground, we're not even plotting the MCC, so what's going on there? I think that's a case where we need to look at the phase protection as well. And we'll see coordination for the single line to ground faults between the MCP and the upstream main. Now this is the one I want to look at. For the settings on the MCP. Yeah, so it doesn't have a specific ground setting, and we're looking at the response of the system to a single phase fault. So we have to look at the phase. Looking at the ground fault settings of the breaker upstream, we can see it does have the ability to plot a TCC. Again, it doesn't have the in and out feature associated with it. So the bottom line is you're going to have trouble coordinating with molded case circuit breakers in series unless the manufacturer has tested that specific combination. And the series, the neutral ground feature works well as far as protecting the whole system, or giving us more flexibility in protecting the system. So yeah, the other point that I would make is that the sequence of events help us kind of highlight an error or a problem early on without having to go through the full coordination procedure. I think that's what I wanted to cover today. Sorry if it wasn't that comprehensive, and I appreciate your attendance. Certainly if you've got any questions, be happy to address them. We may not be able to do it online. Be sure to check in on the EasyPower website. We will be starting to do live arc flash workshops in localized settings, probably in the fourth quarter. And we continue to do regional settings online. And then in the fourth quarter, we'll have a session in Portland. Thank you for attending, and we'll look forward to talking to you later in the month.